So now that we've learned to represent the particles that fly out of a nucleus, alpha, beta, gamma, positron, neutron, in the same way that we represented nuclei last week, that is with a symbol containing a mass number and an atomic number, we're going to be able to put them on even footing and figure out what is made when a decay process happens, and even a little bit of the logic of why certain decay processes happen for certain nuclei. To do that, we need to learn to balance equations showing the before and after picture. And so the basic idea will be that we're going to look at everything that's on the before picture, the mass numbers and the atomic numbers, everything that's on the after picture, again, atomic numbers and mass numbers, and we're going to make sure that everything here adds up to the same thing as everything here. That's how we're going to do it. It's going to help us identify whatever's missing and come up with balanced equations. To the worksheet. So what you'll see here on this worksheet are a set of partial nuclear decay equations, and we're going to complete them, and in doing so, identify what type of decay process is happening, alpha, beta, positron emission, or gamma. Now, the first thing I want to point out about A is that it's worth thinking for a second about what is present in each of these nuclei. We'll do that before we actually balance it. So briefly, appealing to what we did last time, how many protons and how many neutrons in this? How many protons, how many neutrons in that? Pause the video and jot it down for yourself. Okay, I hope what you came up with is 20 protons and 27 neutrons in the calcium, and then 21 protons and 26 neutrons in the scandium. And I want this available because once we figure out the type of decay it is, I want you to see exactly what it does. So, to balance the decay equation, remember, we want everything on the left, mass number and atomic numbers, to add up to the same thing, respectively, on the right. Now, there's only one particle on the left, so what that tells me is that whatever this particle is, I have to be able to add its mass number to 47 and get 47, so that's easy. Mass number 0. And then I need to take its atomic number and add it to 21 to get 20. So think that through for a second. If x plus 21 equals 20, that means x has to be negative 1, because 21 plus negative 1 gives me 20. If we look back at the last video, what we can identify that as is an electron, and that means this is beta decay. And so take note of the really wacky thing beta decay does. We said it was a little strange seeing an electron fly out of a nucleus. Well, the reason that happens is because of what's referred to as a quantum tunneling process, by which one of the neutrons has become a proton, right? I started with 27 of those and 20 of those. When I'm done, I still have 47 total particles. That's why the mass number didn't change. But I now have one less neutron and one more proton. So this will move me to a new element on the periodic table. Notice that the symbol changed. But in doing so, will leave me with the same mass number. So that's where this symbol is coming from. And if you think about the fact that I went from neutron to proton, take a look in the back of your book. A neutron is a little bit more massive than a proton, and it has no charge, while a proton is supposed to have positive charge. So the thing that comes out needs to be very tiny to make up the difference in masses, and it needs to be negatively charged so that I didn't suddenly create new charge where there was none. I've made a positive thing, and I've also made a negative thing. Now to do the rest of these, at least the identification of decay should be easy because you can already see the particle. This, I hope you're identifying already as an alpha particle, so this is alpha decay. And this guy with the +1 as its atomic number is not hydrogen, because if it was hydrogen, it would need to have at least 1 for its mass number. That is a positron, and so you could call this positron decay, or this is a bit more like what you'll hear in medicine, positron emission. That's what this is right here. So positron emission, alpha decay, and over here, beta decay. Now let's go ahead and finish this thing up. For each of these decay reactions, if I have 213 as my original nuclide's mass number, so that this is astatine, by the way, and 85 as its atomic number, that means whatever this is has to add to 4 and 2 to give me 213 and 85. So just doing the math then, 213 minus those 4 that came out is going to give me 209 for the mass number. 85 minus the 2 protons that came out is going to give me 83. And if I look this up in the periodic table, you will find Bi as the symbol. So astatine becoming bismuth. Bismuth is actually a very common endpoint. It turns out this bismuth 209 is the heaviest stable isotope in all of the universe. Anything with more protons or neutrons than this is generally going to decay right away into something else. So maybe not right away. Some of them last a while, but they will eventually undergo some sort of radioactive decay. Finishing up with this one, in this case, I now can see everything on the right side, so I'm going to add all these up, and it'll tell me what I should have on the left. So 11 plus 0 means that positron emission didn't change my mass number, but 5 plus 1 means that I should have 6 protons. And so this would be carbon 11 in this particular spot. In fact, carbon 11 is used in a variety of brain scans. And we're going to talk more about carbon 11 in later problems in this class. It's a very interesting isotope. But this is what it does once it has been created. It undergoes positron emission and is frequently used in what are called PET scans. That's not something that you do at the veterinarian's office. A PET scan stands for positron emission tomography. And so this is what's going on there. Now I've provided 2 of these here that I want you to try to come up with from scratch. Pause the video and take your starting nuclides here and have them undergo each of these 3 processes. It's going to create one of each of those particles in each case and see what you have left over. Pause, give it a go, come on back and we'll do the answers. Okay, uranium-239. You'll notice in this case I've left out the atomic number, but that certainly shouldn't stop you. You can always go to the periodic table and find that uranium has 92 as its atomic number. Same thing here, neptunium is right after that, 237, but an atomic number of 93. Nitrogen, meanwhile, being a different isotope of nitrogen, N13, we know that its atomic number is 7. And even though it may not appear on these, if you're asked to write a balanced decay equation, put in the atomic number. It's going to make your life a lot easier. Every one of these decay processes is going to involve something coming out. So a beta particle, we said, is 0, minus 1, and E. Positron is 0, plus 1, and E. And an alpha particle is a helium nucleus, 4, 2, and helium. And now we just need a daughter nucleus that accounts for whatever is missing after we use this. So in this case here, I need something that I can subtract 1 from to get 92. So this would have to be 93, excuse me, as its atomic number. 239 still as its mass number, because remember, beta decay doesn't change the mass number. It simply flips a neutron into a proton. And this would in fact be neptunium right here. Now, neptunium-237 undergoes a different kind of decay. It does alpha decay. In this case, I need something here that I could add 2 or 4 to and end up with 93 and 237. So just like we did with the bismuth up here, we're going to have 233, we're going to have 91, and that gives us Pa, known as protactinium. Lastly, with the nitrogen, same as we did with the earlier one here, actually not quite the same, because in this case we knew what the daughter nucleus was. Here we want to know the daughter nucleus, and so I need something here that still has a mass number of 13, because this can't change it, but I need it to have 1 less number as its atomic number, because I need 1 plus it to equal 7. So this will be 6, and that will be carbon 13. So that's how we put these things together. The last video we have is going to be a brief one where we look at this problem involving the way that iodine-131, a very important isotope for thyroid cancer sufferers, is made. Come on back and check that one out when you're ready.